systems, if we know this quantity. If you, for example, go and buy a car, in the manual of that car, it's written how much power the engine can deliver. Now, the reason for this is that you can figure out how much work this engine is capable to perform. By definition, power is the rate at which work is performed. So, and I already told you this once, whenever we have rate of changing certain quantity, it is derivative of this quantity with respect to time. So if I want to, so by definition, I have to consider power is an instantaneous quantity. So for example, the manual of a car tells you what is the maximum power. If you don't push the acceleration pedal to the floor, the power delivered by the engine will be small. When it idles, for example, the power is very small. Anyway, so what you have to, if you look at the definition, it's a quotient of differential work over differential time. So you have to consider at a particular instant, you have to consider how much work something does in a tiny amount of time. It will be also tiny amount of work. Then you divide this tiny amount of work by tiny amount of time to get power. Usually we go the other way. We determine power of well, things like motors and engines, and then we can find out how much work this thing is capable of performing to achieve appropriate effect. The SI unit of power, this is a mistake, is 1 watt. And 1 watt corresponds to a rate that 1 joule of work is done in 1 second. Now let's try to find out what is about 1 joule. So if I pick up an object which has mass of 1 kilogram, so this will be about 2 pounds. So if I lift this, so 1 kilogram, and if I move it just 1 meter up, so from there from the floor, for example, to about this height, how much work am I going to perform? Well, mass is 1 kilogram, so the gravitational force is 10 newtons. I will have to apply an upward force of 10 newtons. If I raise it by 1 meter, so the work is going to be 10 joules. So if I lift this thing in 1 second, then this will be 1 watt. So it's not 1 watt, as you see, it's not that much. You have no problem to deliver power of 1 watt. Yes.
Well, you just said it was 10 joules.
10 watts. Sorry. So this was 10 watts. Correct. Thank you. All right. Often we need to calculate it the other way. So if we know what is the function representing power, how power varies with time, then amount of work performed on an object is going to be equal to, well, if I look at the definition, differential work is equal power multiplied by the differential time. So if I add over the instances in which I'm interested, then I will get work. Now, one more thing which I would like to point out. Well, work, due to a certain interaction, is equal to a scalar product of force and displacement, differential displacement. So you can look over here that this is F times dr, scalar product. Now, dr over dt gives me what? dr is displacement of a particle. Velocity gives me velocity of the particle. So if on a certain particle we exert a force F and the particle moves with velocity v, then this scalar product will give us power. All right, so this is how we can calculate work when we know time dependence of power. Yes?
The blank W is work and the blue one is watt.
Correct. That one is 1 watt. This one is work, not change in work. Remember that? Delta W does not represent change in work. It represents work. It is work done in the time interval delta T. Delta only indicates that it corresponds to a particular time interval. We don't have change in work. So if you wrote change in work on the quiz today, then it was incorrect. All right. Now, there is another place actually where we calculate work in a very easy way. There are certain types of interactions referred to as conservative interactions, and for conservative interactions, calculating work is very simple. Well, first I will define what a conservative interaction is. So, if we have certain type of interaction that no matter how a particle moves or an object moves from one location to another location, the amount of work due to this interaction is going to be the same. One of the examples is gravitational interaction. So, for example, if I pick up an object, let's say that object is over here, and I moved it up to that point. Well, Earth performs certain amount of work. And by the way, was it positive or negative? Because why positive? Because force was down, and all the displacements were up. So scalar product of force and differential displacement was always, how come? How come positive? If two vectors are opposite, we have to multiply magnitude of the first vector times magnitude of the second vector. These two numbers are positive, so product is positive, times cosine of the angle between them. Angle between them is 180 degrees. Cosine of 180 degrees is -1. Right, so the gravitational work is negative. When the object moves from this location to this location, the gravitational work is negative. I performed positive work. Do you see that? Yeah, because I was pushing it up. I was pushing it up and the object moved up. So my work was positive. Now I know that actually you think that I raised that object, right? Who actually raised that object? Who determined actually how this object moved? Me or the Earth? Well, we both did. If I apply the same force as I was applying and Earth was doing nothing, that object would be moving with a much higher acceleration upward. I was raising it, it moved with approximately constant velocity, which means that but why did it move with constant velocity? Because the two forces, force exerted by me on this object and force exerted by the Earth on the object, cancel each other out. So if Earth were not helping me, and I apply the same force, the object would move with constant acceleration. Do you see that? Always remember that it is not that a single force moves the object. It's the net force. All the objects together always move the object. Well, anyway, but this was just a digression. Let's come back to conservative interactions. Oh, yeah, so Earth performed certain amount of work when the object moved from that location to this location. However, if this object moved like that, from initial location to the final location, Earth performed exactly the same amount of work as before, no matter along which path. Yes, so if work done by a certain interaction on an object moving from one position to another position is independent of the path, then this type of interaction is called conservative interaction. All remaining interactions are referred to as non-conservative interactions. Well, what is the advantage of having conservative interaction? Oh, by the way, one of the conclusions from the definition is that work done due to conservative interaction along a loop is therefore 0. Well, can you find it out? Yeah, so in other words, if I take this object over here and moved it like that, yeah, so the object moved in a circle, came back to the original location, gravitational work was 0. Can you give me a good argument based on the definition that it's 0?
The work you're using to raise it up this half is equal to the opposite work.
Well, so how do you know that? First of all, how do you know that? And another thing we are talking about, because, what's your name? How?
Harrison?
What's the first name?
That is not the name.
Harrison. Oh, Harrison. Okay. So Harrison said that because work which I perform on the way up is opposite to the work which I perform on the way back. And I said that he's considering wrong work. Why? Because I was talking about which work? Gravitational work, right? Not work performed by me. Work performed by the Earth. Although Harrison could also say actually that the work, gravitational work over here from this location to this location is opposite to that one. But how do we know that? Well, it's not trivial. Really, we will have actually to verify that gravitational interaction is conservative interaction. But I want you to find another path from this location to this location for which it is obvious that the work is 0. Well, look at these two paths. One is like that, the one which I've shown you. All right, and the second one is like that. Along two paths, object ended up at the same location, right? If interaction is conservative, it means that work is, due to this interaction, is 0. Well, how much work was done in the second case? Why? Because the object didn't move, right? The path actually was a point. It also satisfies the condition that it is it starts and ends at the same point. So therefore, work along a loop is always 0. Actually, if we write down, if we chosen this statement as the definition, then this statement would become a theorem. Yeah, because now think about that case. Yeah, I will now move this object that way. Right, so how much work was done? 0. All right. Now there was a certain amount of work done by gravity or by the Earth when the object moved from this location to this location along this path, right? Now, therefore, how much work was done along that path? So that the combined work was 0. And so let's say that to move, when it was moved from here to here, let's say that this was 2 joules. Earth performed work of minus 2 joules. And so how much work it has to do on the way back? 2 joules. So that in the loop, it's 0. Do you see that? Right? Well, so work along this path is 2 joules, and along this path is minus 2 joules. So how about along this path, if it moves in the opposite direction? Will be opposite to the 2, right? So it will be minus 2, right? Which means that along this path it was minus 2 joules, and along this path it is minus 2 joules. So then no matter along which path we move, the work has the same value. And here are the gravitational interactions which are actually in our material. We'll talk about gravitational interactions. So remember that gravitational interaction is conservative. Elastic interaction, elasticity is conservative as well. So for example, spring, the force which a spring exerts on something is a conservative interaction. In the future, next semester, we are going to talk about electrostatic interaction, which is also conservative. Well, for conservative interaction, we can introduce a quantity which, Harrison, are you lost? Are you fine? Okay.
What was the last one? Sorry, I said gravitational elastic.
Electrostatic. We will discuss this during the second semester, but it's good to recognize. In this class, I want you to recognize that gravitational interaction is conservative and elastic. So if we stretch spring, for example, or bend something like an arch, for example, a bow, if you can change the shape of the bow and then it comes back to its original shape because of elasticity, and these forces are also conservative. For conservative forces, and only for conservative forces, we can introduce a concept which is called potential energy. And the purpose of having concept of potential energy is to simplify calculating work. By definition, potential energy is introduced in such a way that if an object moves from one location to another location, conservative work is opposite to the change in potential energy. And if we integrate it, actually we will have, so if I move from one location to another location, then change in potential energy is opposite to work. So now coming back again to this case, to this mouse. So if a mouse moves from this location to this location, work done due to gravitational interaction is opposite to the change in potential and gravitational potential energy of this object. So in the future, rather than integrating along the path, what we are going to do is, well, we will derive formulas. We will learn formulas which will tell us what is potential energy of an object at every location. So then I know what is potential energy here and what is potential energy here. So let's say that over here potential energy will be 7 joules. Over here will be 5 joules. Then I will know that if object moves from this location to this location, gravitational work is opposite to the change in potential energy, which means how much work was done? -2, right? 7 minus 5 gives us 2. So change in potential energy is 2 joules. I have to take opposite value of that. So it will be -2. Do you understand the advantage of it? We avoid what? What can we avoid that way? We have to do it only once, and usually it is that somebody already has done it for us. We don't have to repeat it every time. What? When we calculate work. Because normally how we calculate work? Harrison, you have an idea? What is work? How do we calculate it? Not force times distance. This is high school definition. No, it is work energy theorem. It says how work is related to change in kinetic energy. So we don't use, we actually try to find out work in order to find out what is the change in motion. Not that we consider change in motion. Yeah, it's easier. Yeah, because I mean, we can find out how much work it is required to move a spacecraft from here to the moon. We can figure it out directly, not from this how a spacecraft moved, but from the configuration of the objects. We know where Earth is, we know where Moon is, so then we can find out how much work will be needed for that, and we will design rockets appropriately to perform that work. Well, how did we calculate work yesterday? Force times differential change in position gives us differential work. So along tiny fragment of a path, force times displacement is equal to the work. How about along an arbitrary path? We have to integrate it. We have to add all those differential works. Correct. So whenever we calculate work, we have to integrate force. Well, we would have to do that if we did not introduce concept of potential energy. Because now when we introduce concept of potential energy, how do we avoid integration? We just calculate a difference in potential energy and have work right away. Now you can, this definition actually assigns potential energy with accuracy to a constant. And this is how we know potential energy. We never know potential energy. I mean, we can assign any value to potential energy we want. However, if we assign a certain value, then we have to be consistent. So for practical purposes, recognize that we do it in such a way that we first choose a point in space which we call the reference for potential energy, to which we assign potential energy 0. So for example, I can say that, that at this location my gravitational potential energy is 0. Then consistently when I move somewhere, I change potential energy. So for example, well, how about if you figure out what will be my potential and gravitational potential over here now? More or less? How do you know that it is more? Because I'm higher than the reference point, so what? So gravitational work was 0. I mean, probably it will be easier to understand. How about if I over here have potential energy 0? Now I will get up. How much work did the Earth perform on me? Positive, negative, or 0? Negative. Why? Because I moved up, force was down, right? So angle was 180 degrees. So magnitude of the first vector times magnitude of the second vector times cosine of 180 degrees gave me negative value. So gravitational work was negative, which means that the change in gravitational potential energy is positive, right? Because it says over here, over here better, change in potential energy is opposite to that work. The work due to conservative interaction, not work done by the floor, though. You have to be careful about that. All right, now I can actually say, well, now I want to choose this step as the reference for potential energy. So my location now, I want to have gravitational potential energy 0 now. And I can do that consistently. What will be my potential energy now? Positive, negative, or 0? Negative, right? Because now when I went down, force was down and displacement was down. Cosine of the angle between them were 0, which cosine of 0 is 1. So gravitational work was positive when I went down. Consistently with the definition of potential energy, change in my gravitational potential energy, therefore, was negative. So I lowered my potential energy. All right, and because our purpose of having potential energy is to calculate work, we don't care about that constant. So always choose a reference for potential energy in such a way that the formulas are simple. Do you understand me? All right. Why don't we take a look at some examples? So how about if we consider indeed an object above grass? So here is your lawn, and there is a stone above your lawn. What is its gravitational potential energy? Well, what do you say? First, we have to assign the reference point. Very good. How about if I say that when the pebble is on the lawn, its gravitational potential energy is 0? Yeah, so I introduce coordinate system. This is x, this is y, and at the origin I choose gravitational potential energy to be 0. Well, consistently, now, when that object moves by a certain displacement dr, well, gravitational force is downward, so I can now find out that gravitational potential energy at that location, well, it is gravitational potential energy at this location minus gravitational work when the object moves from initial location to the final location, right? You can look at this, that if you move this term to the left-hand side, you will have change in gravitational potential energy is opposite to the gravitational work when it moves from the reference for gravitational potential energy to the point at which we want to assign potential energy. All right, now for simplicity, I will say that gravitational potential energy is 0, so this value is 0 for me, which means that I'm left only with the gravitational work. And, well, gravitational force was approximately equal to the weight on Earth, so I can write that this is mass multiplied by acceleration due to gravity. What product do I have here, by the way? What multiplication between m and g? How many multiplications do we know? 4, correct. Which one is that? Number multiplied by a vector, correct. The result is going to be a vector, correct. All right, so now I have to multiply this product by differential displacement. Yes, so I multiply this vector by this vector. What multiplication do I use? Not vector multiplication. Scalar product, correct. The result is going to be a number, correct. So this expression is a number. If I add the numbers, I'm going to get a number, correct. All right, so let's now calculate that. Well, I can write down scalar components consistently with this expression over here. So for dr, I will have that there is a scalar component in x direction is dx, in y direction is dy, and z direction is dz. How about if I write it down on the whiteboard so that you see what I'm talking about? Yes, a vector dr, scalar components of vector dr have 3 components in general. Now, weight, what are the scalar components of weight? Consistently. X component is 0. Y component is how much? Negative mg. And z component? 0. Okay, can we multiply these 2 vectors then? How much am I going to get? If we know scalar components in a Cartesian coordinate system of the 2 vectors, how do we multiply them? How do we find the scalar product? It is as important formula actually as knowing magnitude of the first one times magnitude of the second one times cosine of the angle. Can we multiply these two vectors? Mark, can you do that? 0 times dx plus second component times second component plus third times third. So the result is going to be minus mg dy. So this is the result of scalar product. Now I have to vary from this location to this location, and the variable of integration is y, which means that I'm going to calculate from original y component, y component of original position, and here I will have y component of the final position. All right, let's now integrate that. So minus and minus cancels. M, is it a variable or constant? Constant. I can take it in front of the integral. G, is it constant or variable? Constant. I can take it in front. So I will have integral of dy. Let's use fundamental theorem of calculus. Integral of dy is y, correct. Integral of dy is y. Now I have to plug in the values. And when I plug in the values, I will get that the result is mgh. What did I find? Actually, change in potential energy from what point to what point? From the reference point. And actually, well, I calculated work, and I assigned 0 to this one. Therefore, change in potential energy is equal actually to potential energy. Right, because the change in potential, correct, this is change in potential energy from this point to this point. And at this point, we assign potential energy to be 0, which means the difference between potential energy at this point and this point is the same as just potential energy at this point. So we derive an expression for gravitational potential energy. So it depends on the altitude above the reference point. So if I walk, let me give you a few puzzles then. If I walk from here to here, how much work did Earth perform on me? None. Why? Because directly from that, my potential energy, I did not change my elevation above the floor. Right? So if I assign 0 over there to my potential energy, gravitational potential energy, my gravitational potential energy over here is also 0, and work, therefore, is, well, opposite to difference between these two zeros, so it's going to be 0. Well, however, let's try now, I'll do something else. Now I will walk a more complicated path. How much work did Earth perform on me now? 0, right? And did you see how complicated was the integration? We didn't have to integrate now. Do you see that? We calculate work by taking difference in the two potential energies. Right? So this is advantage of analyzing conservative interactions separately. However, we have to memorize something. What? That, correct. We have to memorize the formula which says how potential energy depends on location. Well, if we are close to the ground, to the surface of the planet, then we see that gravitational potential energy is a linear function of elevation. So if I make a plot of it, it's a straight line. The higher we go, the potential energy changes proportionally. Well, how about if we take a look at the gravitational potential energy of a planet? Yeah, around us. Well, what's the difference now between this situation and the situation a moment ago? When I stick close to the surface. Not only that, I mean, how do you know that I'm going to take a different reference frame? Maybe I'll take the same reference frame, however, something else is different. Well, within the volume of this building, wherever you go, gravitational force exerted on you has the same value. You weigh the same. I mean, your weight here is the same as on the top floor. Well, however, if you are at the surface and then you fly 200 kilometers on the orbit, your weight changes, and not only that, the gravitational force exerted on you changes. What law, by the way, describes that? How it changes? We have to be fast in that. Correct. Newton's law of universal gravitation. Correct. All right. So, well, gravitational force is toward the planet. Now, let's say that we start thinking the same way, almost like before. That what happens if we displace it by this amount, by vector dr. So, in order to find out gravitational potential at an arbitrary location, from the reference point, so changing gravitational potential energy from the reference point is going to be opposite to the gravitational work. So I put minus because it is opposite to the work. Now, minus gravitational constant, mass of the planet, mass of the object, divided by the distance from the center of the planet to the object, multiplied by this unit vector pointing radially from the planet. So this gives me the gravitational force vector. Now I have to multiply it by the displacement vector. And again, if I think about this direction being r, now the displacement, I mean this vector is, hold on. Did I confuse the signs here? No, okay. Vector r is away from the planet and dr is away from the planet, right? So it's magnitude of the first vector times magnitude of the second vector times cosine of the angle between them. What is the angle? 0. So cosine of 0 is 1. So in the result, this scalar product gives me just dr. All right, now the rest is math, right? We have an integral which we have to integrate, and I decide now about the variable of integration. Let's use this distance from the center as the variable of integration. So at reference location, let's say that that distance is r0, and we will figure out where to choose this reference and the location at which we are trying to determine the gravitational potential to be r. All right, so I can pull out minus over here, so it will cancel with the other minus. Can I pull out g from that integral? Is it a constant? Yes. How about capital M? Yes. How about small m? Yes, it is mass of that object which is raised. How about r squared? No. What is r squared? And it's not radius. I remember not to associate r with radius. Most frequently it is related to position or distance. Over here it's a distance. of the object from the center. And as it moves from the reference point to the considered point, it changes. This distance is changing. So it is not constant. We cannot pull out that. So we can pull out g, m, and m, but not r squared. So we have integral of function r to minus 2. Well, there is now this minus cancels with this minus. Now indefinite integral of r to minus 2 is how much? I mean, this is the first formula which I wanted you to learn in the appendix of the indefinite integrals. And indefinite integral, I mean, that formula says that integral of x to n dx, indefinite integral, is x to n plus 1 over n plus 1. Now our n is minus 2. So indefinite integral will have x to minus 1 divided by minus 1. Do you see that? All right. So from that minus 1, I got one more minus. So I had three minuses. I had this minus, and 1 came up from integration of r to minus 2. And r to minus 1 is 1 over r. So I wrote again 1 over r. All right, so I have now to plug in the limits when I use the fundamental theorem of calculus. So when I plug in r from the as a top limit, I will have 1 over r. Now, in principle, I should have here r0, point where the reference, where I choose the reference. Now, we should be smart and choose the reference in a convenient way. A convenient way would be such that the formula is the simplest. Where to choose the reference for potential energy, then? All right, for example, 0, because it's easy to calculate, right? Yeah, because then we will have formula 1 over r minus 1 over 0. And 1 over 0 is how much? It's easy to calculate. 1 over 0 is not 0. It's undefined. 0 is not a good reference point then, because we are in trouble to determine what is. I mean, 1 over 0, you can think about that it's infinity. So we will have formula for gravitational potential energy that this is infinity or minus infinity plus 1 over r. It's really complicated formula to work with. Find another reference point. 1, because it's easy to subtract 1. 1 what? Kilometer or meter? Yes, so the formula would be 1 over r minus 1. And why 1 is simpler than 10? Actually, 1 is not a good reference point. We can find a point where the formula becomes simpler. Infinity. Yes. Choose a reference point for gravitational potential energy at infinity, because 1 over infinity is 0, and the expression for gravitational potential energy is, in this situation, is minus g, gravitational constant, mass of the planet, mass of the object divided by the distance of the object from the planet. Now, I still want to ask one more puzzle about it. Well, yeah, because in the previous situation, we selected gravitational potential energy to be 0 at the surface. See what will happen if I decide in this formula to have it on the surface. So in other words, what should I put as the denominator over here? Yes, Taylor?
No, I was asking, why does it make different than what?
I will explain it to you later, okay? Because I have already told you, explain, but I see that you missed it. All right. How about if we think now, concentrate now, what should I put here if I selected R0 to be on the surface? What value should I put here? Radius of the Earth, correct. Well, if I, and actually, how about consistently, this distance from the center, I will call that this is radius from the Earth plus the height above the surface. Right, so here I have 1 over r, 1 over the distance of the object from the center, minus 1 over radius of the Earth. All right, now I will find a common denominator. What's the common denominator of those two? A product of those two. Right, so I will multiply this fraction by r and this fraction by r plus h and combine them. Now this r and this r cancels. And actually over here, if I don't move high, this expression is practically equal to the radius of the Earth. So I can write down that this is mass of the object times gravitational constant times mass of the Earth divided by radius of the Earth times h. Yes, I have m expression g, h. If you plug in the numbers for gravitational constant, mass of the Earth, and radius of the Earth, do you know what you are going to get? What will be that value? How much? It will be acceleration. It will be 9.8 meters per second squared. This expression is g, which means then we got an approximate. This is over here. We made approximation, right? So now which one is more accurate? Which gravitational formula for gravitational potential energy? The one which we just derived, or the previous one? No, that one. The other one is approximate. The other one is approximate provided that you don't go too high up, so that you can assume that the gravitational force does not depend on your position. All right, so this will be all for today. See you Monday.
I'm ready to take that test now.